Morning. Welcome to Krishna's class. Last time we looked at the evolution of the Lebesgue integration, and we have finally defined what the Lebesgue integral means. And then we asked the following question: is it possible to characterize the Lebesgue integrable functions in a different way? That means more easily, something like, say, all continuous functions are Lebesgue integrable on bounded intervals. I mean, this is my sample of this kind of results. Okay. So we have to say that a theorem of the type f with certain properties, then f is Lebesgue integrable then only if certain conditions are satisfied. So that equivalent statements to Lebesgue integral. And we have seen it for Riemann integration, and we in fact stated both the conditions, but we didn't do a comparative analysis of the two. So let us do that first and then go over to the next stage. The next stage is to look at what is the fate of the fundamental theorem of calculus in the context of the integration. But before that, let us just look at the Riemann integral and the Lebesgue integral, and then have a comparison and say what we get out of it. Okay. So let me just recall the characterization of Riemann integral functions. So we work first with the Riemann integral. We said that if f is a function from a bounded closed interval AB or a compact interval AB, f bounded then these are the preconditions. Then f is Riemann integrable if and only if the discontinuities of f is a set of and in fact, if you recall, when we consider the details of the Riemann integration before introducing the Lebesgue integration, that means we had not at that time talked about sets of measure 0. Then we described it by packing the set of discontinuities into intervals such that the interval lengths shrink to the total length of such intervals shrink to 0, or you take the infimum of that, and the infimum of that should be 0, or what you call the null set. You are talking about the null set, and we demanded that the set of discontinuities of the bounded function defined on the closed bounded interval is a null set. So that is the language that was used. Later on, found that this is exactly the same as what we are now familiar with, namely the sets of measure 0. Okay, so that's a comment about that. Now you see that what is the corresponding result or analogous result in the context of Lebesgue integral. We take F, okay, E is a subset of R with measure of E is finite, it's a condition on that, and then F is a real valued, bounded real valued function from E to R, F bounded then F is Lebesgue integral if and only if, very simple, F is measured. So all measurable functions defined on subsets of R of finite measure which are bounded are Lebesgue integrable. Conversely, in the case of bounded functions defined on sets of finite measure, the Lebesgue integrable functions are all measurable functions. Now we make some little remarks before we proceed further and look at some examples. This we have considered earlier. But not in our last lecture. So if you take the characteristic function of the interval of the set of all rational numbers, so this is of course a discontinuous function and discontinuous at every point, and the function takes only two values, namely 0 and 1. This is the characteristic function of all rational points in the interval 0 to 1. Now, F does not belong to Riemann integrable. F is not Riemann integrable over 0. Why? Because if you go to the construction of the Riemann integral, you will see that in this case the lower integral LF, this is the lower integral, or I will put it this way, integral uh, the lower integral. Lower integral of f. This is equal to 0. Go to the definition. Then you see that the upper integral over 0, 1 of f. I can write this way. I think the notation that we had was this one and the upper integral was this. Okay. So this is less than this equal to that. So that is the problem. The lower integral, the lower sums were all equal to 0. The upper sums were all equal to 1. Therefore, the lower integral, which is the supremum of all lower sums, is 0. The upper integral, which is the infimum of all upper sums, is equal to 1. So they are never equal, and the reason for that is every interval contains both rational and irrational terms. This is called the Differential function. So the Differential function is not Riemann integral. But now look at this, the same thing. However, f is Lebesgue integral. And you can see that this is actually f is equal to one times chi of q complement. Okay. That is, it is 1 on the set 0, 1 intersection q and equal to 0 on the interval 0, 1 intersection q complement. Q complement is the set of all irrational. So at all irrational points, the function is 0. At all rational points, it is equal to 1. Therefore, you see that f is a simple function. So in fact, we can write down the integral of this. So integral, the Lebesgue integral of over 0, 1 of f equal to 1 times the Lebesgue measure of plus it's a sum of step functions with coefficients as 1 and 0, and you see that this is equal to 1 times measure of this is 0 because this is a countable set, and the Lebesgue measure of this, that is the complement of this set of 0 measure, therefore it is which is equal to 0. So this is the Lebesgue integral of fx, and that's equal to 0. Okay. So the moral of the story is that we get some reach beyond the Riemann integrable functions. In fact, we have earlier shown that all Riemann integrable functions all bounded, I mean, naturally, one of the conditions for Riemann integration or the whole theory works only for bounded functions on compact intervals. Okay, therefore that is built into the theory because we do only for that. Whereas Lebesgue integration theory goes far beyond. That is one thing. And because what are the comparisons? Here we are taking only intervals of the type AB or a compact subintervals of R. Whereas E here that we take is any measurable subset. Okay, so that is one comparison. So and this is a special case of it. Further, we also know that all Riemann integrable functions, so this is one of the early things that you prove, all Riemann integrable functions are Lebesgue integrable functions. Okay, so just recall this, that all Riemann integrable functions are Lebesgue. So it's a Larrain class of functions. So it is defined for bounded functions. I mean, here it is not only defined for bounded functions, it is defined for all measurable functions. Okay, in a through 4-stage process, we have arrived at the integral. Under some conditions, the Riemann integral exists, and in the comparative level with Riemann integration, you see that all Riemann integrable functions are Lebesgue. That is one of the early results that we proved to show that we are getting something more than the Riemann integral. And this is a classic example of a bounded function defined on a compact interval, which is not Riemann integral, but Lebesgue integral. And you can easily see this theorem working, this characterization working. So here you see that the set of discontinuities of F is not a set of measures 0 because it is everywhere it is discontinuous. So the measure of the set on which it is discontinuous is 1, is not equal to 0. Okay, so that's the point. So you see that we have all Riemann integrable functions are contained in AB. Okay, that is that. Secondly, in fact, this is a proper curve. Okay, so that's what we have, right? So we have got a genuine extension. Concept of integral. So this is the point. This is the outcome. Okay. Now, having got this, having got this, now what we look forward to is what does so the next question we take up, what does the fundamental theorem of what happens to the what about the of differential and integral terms? What is the manifestation of this theorem? In the context of the new integration. That's the problem. Again, we have elaborately considered this and discussed it in all details, but we will just recall it because it is important. Now, as I have commented earlier, Okay, these are the two questions that we consider. Question 1, question essentially the same. Okay, so this is our next topic for discussion. And why this question comes up? Because if you look at the classical notion of integral, see, when we did calculus, we first learned the concept of differentiation after introducing the concept of limits. And then we looked at all the classical functions like polynomials, first constant function, polynomials of higher degree, then exponential function, logarithmic function, and then we had looked at the trigonometric functions, and then all sorts of combinations of these functions using addition, multiplication, and then what you call function of a function rule, and then and so on. We had very nice results, and in fact it looked as though, or at least the student at that stage, at that level, just walks out by the feeling that all functions can be differentiated, unfortunately. And later, when he does more deeper mathematical concepts, he realizes that this is false. Okay. But having done this, we start the integral calculus. In the integral calculus, the concept of integration is presented as an inverse process of differentiation. So, concept of integration as the inverse process of course, the constant functions have derivative 0. So, the integral of 0 would be naturally any constant. And then you take polynomials, you know the derivative. From the derivative, you can cook back the what is called the antiderivative. So, this was used. So, all this then, of course, further inroads into mathematical analysis showed that this is probably a very crude notion of differentiation and integration, and possibly the integrals, the concept of integrals have to be reworked. And that led to, so geometric interpretation of integral. as computation of the as the area. I don't want to say more. It's the area enclosed between the graph of the function, the ordinates, and the x-axis. Okay. Now the question comes back to you. How this computed the antiderivative and the integral are related. How? The sense of Riemann. So we slipped from a very happier position into rather a complex environment. It's not too straightforward. Okay, so even the very word antiderivative itself is not sensible universally. Okay, so that is what we found at that stage. And there are very nice theorems connecting, Riemann integrable functions, how they are derivative, or in short, this is the relation that you are asking. Suppose f Riemann integrable over the interval A, and therefore you define this is well defined. This is well defined. I mean, I am talking about the Riemann integral, this way, or if you are, I can put this way, Riemann integral of f t dt. This defines a function on the interval AB. Now, the question that you asked was, is this was the basic question that we wanted to ask. If that were true for all Riemann integrable functions, then the antiderivative concept would have been stretched. But then it is not that simple. Okay, so this relationship is not that straight. But then under conditions on one could relate f derivative to, so it is not altogether a hopeless scenario, but there were under conditions one could do this. For instance, all smooth functions f. Okay, you can define the Riemann integral on compact intervals, and then you can integrate them and get capital F. In that case, capital F equal to capital F derivative is equal to small. I mean, that's a very generous, smoothness is a very generous condition on the function. But even under lesser conditions, this is possible. So you look at the theorems related to what is called the fundamental theorem of calculus in the context of Riemann integration. Now, having gone beyond that to Lebesgue integration, you would like to see with the new tool that you have in your hand, which in a way supersedes the Lebesgue integration or Riemann integral, what is the status of the fundamental theorem of calculus. So the question here is, between the integral and antiderivative. Poles in the context of the more general integration theory, namely Lebesgue integration. Or we are simply asking what is the status of this antiderivative integral relationship in the context of the Lebesgue integration. So this is something that. So before that, while doing that, we had to do a lot of fascinating analysis. And we introduced two fascinating class of functions, namely functions of bounded variation absolutely continuous functions. In fact, you know that all continuous functions need be differentiable. One can construct a continuous function or a function on a compact interval which is continuous everywhere but nowhere differentiable. That is possible. So how do you recover that function when you don't know what the derivative is? Simple. So, okay. So for such functions, the fundamental theorem of calculus does not hold at all. Okay. So it is not possible to, if the function is n times differentiable, there is no guarantee that the n plus first derivative exists. That may not be possible. That's the problem. Okay, right? So we have to really restrict to functions for which the derivatives do exist. Then only you can pull back the function using integration from the derivative, if at all it is possible. So this is the question that we have to. So the first class of functions, we called it, so BVAB, bounded variation. Let us recall this definition and some results related to that. In fact, before that, not too significant though, but you have what are called Lipschitz functions. This you would have heard in the context of the existence and uniqueness theorem for first order differential equations. So let me write this three classes of functions. One, Lipschitz over the interval AB. Then the functions of bounded variation over the interval AB, and the functions which are absolutely continuous over the interval of. How these three sets are related. So we will define these concepts. So first thing that we look at is define Lipschitz. Suppose f is a function defined, real valued function defined from AB to f is set to satisfy a Lipschitz condition Lipschitz condition on AB if modulus of is for every where k is a constant. Or in other words, what we are asking for is there exists some constant k, okay, a positive constant. There exists a positive constant k such that mod fx minus fy is less than or equal to k times mod xy. Obviously, all functions which satisfy Lipschitz condition are, and then we say because you have ideas like locally Lipschitz, etc., etc. there, but we are now talking about the whole interval. Okay. So you see that f belongs to satisfies the Lipschitz condition implies f belongs to f is continuous. And that's it. This is one of the results that we can immediately get. But there exist continuous functions which are not functions. Take an example. The example is this. If is continuous, but not functions. Not functions. So that's an example. Okay. Now we define what are called an absolutely continuous function. Just a step, some more deeper restrictions than just continue. What you call absolutely continuous functions. On the interval AB. We first define this. Suppose f is a real valued function. Check from the compact interval AB to is said to be absolutely continuous. Provided for each epsilon positive, there exists a delta such that for every finite disjoint collection AKBK of open subintervals of AB divided for each epsilon positive there is a delta positive such that for every finite disjoint collection of open subintervals of AB, whenever then less than epsilon. So this is whenever this is true, then this is true. This is a more stringent condition than continuity. Remark all absolutely functions are all absolutely continuous functions are continuous. So you have this relation that is a proper subset of all continuous functions. So this relation is satisfied. In fact, absolute continuity in the case of a single interval pk is the criterion for uniformity. Uniformity. And this, of course, implies continuity. But the converse is not. That means a continuous function need not be absolutely continuous. Even for increasing functions. Now an example is a very sophisticated example, which will come every now and then. The Cantor-Lebesgue function. I am not going. Is an increasing function on 0, 1, but not absolutely. Go to the proof of this. It's a sort of building up steps from 0 to 1. It's a monotone function. And you see that the differentiability of this function fails on the Cantor set. Okay, which is not countable. And therefore all sorts of consequences are there. And we will go into that soon. Okay, that's an example. So we have now a lot of interesting things coming up, relations. Put some of these results on a theorem. We have this theorem. It's contained in this is a proper content. LIPAB that's a definition. Yeah? So just keep this in mind. Now you see that this function if you take this function That's an example of a function which happens to be absolutely continuous but not Lipschitz. Okay. So now one of the theorems that you can prove here is that structure of such functions, let be f is the difference of absolutely continuous increasing functions. This is the significance of these increasing functions. Okay. That is, f can be written as f1 minus f2, where both f1 and f2 are absolutely continuous, and but also increasing. That is f belonging to maybe and are both increasing. Now this has some significance, as we shall see. Okay. Now we introduce what are called, we visit this result. Okay. Functions are bounded. Or we use the symbol so we take f from so we take f from a compact interval AB let P be a partition of Xn a partition of point. That means A equal to X naught. What's the meaning of that? Now we define variation of f the partition. So we define this V F P defined as sigma now. For instance, suppose you have a function which is behaving like the sine function, and we are calculating it. Suppose we take the variation with respect to these points, say, or I will exactly use sine function. This is now we give a partition by 3 by. What is this number to sum? Now you see V. Okay, for this example, work out the variation. Okay? So we work out the variation of where P is equal to 0, pi by 2, then 3 pi by 2, 2 pi. This is equal to what? Is the maximum value 1? This is actually 1 plus 2 plus 1. That's the variation. And that's the maximum variation that you can have for V, for sin x on this interval. Okay. Whereas suppose you were to take some other partition, then you can actually see that it could be less than this number. So you see that in this case, you see that variation of zero to 2 pi. Okay. And now we define the total variation. This is denoted by V over the interval the total variation is TVF because it is independent of the partition. Supremum of for all partitions now you can easily see that the total variation of sin x over the interval 0 to 2 pi the total variation that you can see. All other variations, if you compute with respect to other partitions, they are all going to be less than that. See, what you have done is, if you just look at this is what happened. You took intervals over which the function is monotone. Okay. So here it is, this is 0 to pi by 2. The function is monotonically increasing, and from pi by 2 to 3 pi by 2, it is monotonically decreasing, and from 3 pi by 2 to 2 pi, it is again monotonically increasing. So here it is increasing, on this interval it is decreasing, and again here monotonic. So if you take such a partition, then you get the what is called the total variation. So one has, if then PV of the total variation of F restrict to so this relation, these are all little things that you can this is a nice this may be useful. Now we define functions of bounded variation. We say that f function of bounded variation. Provided what is that? dV of f is finite. This is the crucial bounded variation class of functions. Now we make some examples. Let f monotonically increasing on, suppose f is monotonically increasing on it. F is from then so all monotone functions on the interval are functions of bounded variation, whether it is increasing or decreasing, right? It is symmetric. Okay? They are all functions of bounded. Another example where even a continuity, see, this need not be a continuous function. Okay? But continuous function need not be a function of bounded variation. Continuous function may not be a function of bounded variation. This is one remark. Take the following example. F so fx you define as pi by 2x, and this is equal to 0. Now you see, you immediately observe that as x gets closer and closer to 0, it rapidly oscillates. But it's a continuous function because of this. You know that cos function is bounded by 1. Therefore, this is continuous. So the only problem is whether continuous at 0. Clearly, zero. But it's rapidly oscillating. So you see that the function is squeezed between plus x and minus x. So it's something like this. Something like this. I mean, this type of functions we have visited several contexts. Now, F is that's the only place where you have any doubt at all about continuity. 0, 1. But why is it so? Take a partition and demonstrate it. Now choose a partition. So let this be the partition Pn. Now you see that Pf Pn is equal to, calculate it. It's very easy to calculate it. This is equal to 1 plus and you see that Vfpn as n tends to infinity is a slowly diverging sequence. Okay. Now we can prove this. Statement that we can make is F is Lipschitz over so even continuity cannot sometimes assure you that the function is of bounded variation. At the same time, there are non-continuous functions or discontinuous functions which are functions of bounded variation. Okay. So, remark. But char of bounded variation. But a function of bounded variation need not be so that is something which you keep in mind. But if it is a Lipschitz continuous, then it is of bounded variation. That is quite easy to. Now, what one can prove is something similar to what we had in the case of absolutely continuous. So, a lemma. I am going through the whole exercise sans the proof. Okay. F belongs to F belongs to BBAB if and only if or implies f is equal to f1 minus f2, where both f1 and f2 are increasing functions, monotonically increasing functions. Monotonic increasing. It's a nice representation theorem which you are assured of. And this is in fact, this is what you can prove, Jordan's theorem. This is a characterization. This lemma is a characterization property. So f belonging to if and only if f is the difference of two increasing functions monotonic increasing functions that is, of course, a beautiful result. Therefore, you see that we have seen the absolutely continuous functions, which can be written as the difference of two monotone functions, and therefore every absolutely continuous function is Riemann where and oops, monotonically increasing. That's a nice representation theorem for absolutely continuous functions. Therefore, we have the following result. What is the result? The result that we have is this. Contain Now this is one nice result. Now we have see all monotone functions are differential. Almost everywhere. That means except possibly on a set of measure 0, the function is differential. Okay, and that's the nature of the monotone functions. You have at most a countable set of discontinuities for such functions because of the monotone nature of the function. So both f1 and f2 have this property. Therefore, what is the consequence? The consequence is this. That is, we have the theorem f belongs to is differentiable almost everywhere on AB. And not only that, f dash exists, therefore, f dash is integrable over therefore you see that if for all of these f belonging to ACAB implies f is differentiable almost everywhere. I'm just applying the theorem for ACAB because ACAB is contained in PVAB. That's the proof. F derivative is integrable and this is a crucial result which we would require in our further investigation on this. I think that is long enough for the day. Thank you very much. Our next lecture will be covering the fundamental theorem for differential and integral calculus. So I will just put it one here and the next one will be 2. Right? So thank you very much.